So we'll move swiftly on to the next presentation, which is Guy Adams from Datalytics. Talking about 98% of your data is worthless, but which 99%? Great. Can't wait to find out.
Hey, good morning. I couldn't really have asked for a better introduction than the one that Professor McFarlane gave, because the areas that we've been focusing on in the last couple of years are people who absolutely identify in that 59% that say there are cost prohibitive elements for this, but we're taking technologies that have been developed outside the manufacturing space, and this is our first foray. So we're very much in that digital technologies that we think can contribute to that cost effectiveness. So this title, 99% of your data is worthless, but which 99%? It's deliberately provocative. Most people react badly to being told that 99% of what they're collecting is junk. Hopefully by the end of this, you'll at least understand the rationale behind why we make that assertion. But before we get into that, look at a couple of use cases. This is a connected car. The data coming off this car should be allowing it to go in for service only and exactly when there's an issue. And the data from millions of these cars should be being aggregated by National Highways Department to build a complete picture of the conditions of their road networks and prioritizing their investment exactly where it's needed and preventing pothole degeneration before they cause damage and accidents. This is a smart factory. The information coming out of this factory should be allowing preventative maintenance to be happening far more efficiently as happening today, and should be allowing operational digital twin models to be being updated in very close to real time to allow all sorts of process improvements and scenario planning. This is a connected aircraft. The information coming off this aircraft should be allowing airlines to spot degenerative failures in flight and have engineers and spare parts pre-positioned at the gate when the aircraft arrives and turn it around immediately, as opposed to having to take that aircraft out of service for 24 hours at the cost of hundreds of thousands of dollars. It should also, and this has been a hot topic recently, it should be allowing, in the case of an actual accident, a crash investigator to be processing the data that's come off in flight within minutes of the incident to work out if it affects other aircraft in the fleet, as opposed to having to wait weeks or months for the black box to be recovered. And my final example here, the connected cow. The information coming off this cow should be allowing farmers and vets to detect the early onset of disease before it spreads through a herd, and should be saving the lives of millions of cows and calves every year who die from preventable labour-related complications. Now, all of these have got that caveat word in should. In the vast majority of cases, this isn't happening. Why? From our perspective, there are two fundamental challenges that are preventing these sort of use cases, this sort of value becoming ubiquitous. The first one is all about data transportation. When we look at the edge, and obviously the edge has different definitions in each of those use cases, it looks something like this. The actual data that's being generated is happening at incredible rates. But we're trying to feed it through something like that. The ability to transport data from the edge is a ratio lower than the rate that's being generated in some industries by 10,000 to 1. You've got to pick one data point in 10,000 because all you have the capacity to transport. Some scenarios are better than others, but there is always a fundamental disconnect between the amount of data we're generating and the amount of data that we can transport. So what are the implications of that? Let's take a scenario where we've got 1,000 to 1. So we're only able to pull back 0.1% of the data. Well, data is all about decision making. Collecting data and not using it for decision making is by definition pointless. Every bit and byte of data we collect, we do with the view to making some sort of decision on the basis of it. So if we're only pulling 0.1% of that data, our ability to answer even basic questions is pretty limited. If I look into questions here, I can tell it's a dog, what species it is, what breed does it bring a collar. I stand zero chance of answering any of those questions using the 0.1% on the left. And this is the premise today. We have a customer in the connected car space. Their vehicle has over 1,000 sensors. They have only a tiny amount of bandwidth, so they're just pulling 10. With no intelligence at all, they're just saying, we can only get 1%, so we'll just pick that 10. So they're just selecting one very, very small area of the data. What we do with the gallium technology is turn that on its head a little bit and saying, rather than collecting a subset of the data at very high accuracy, let's take a small accuracy hit, maybe 1 or 2%, so we guarantee 98 or 99% accuracy, but in exchange we can pull a far bigger overall percentage of the data set. So the image on the right here is a little bit blurry. We've sacrificed a little bit of accuracy, but I can still tell it's a dog, I can still tell what breed it is, I can still tell whether it's wearing a collar. Now, there are always people that say, oh, but there are questions you can't answer. Tell me what color eyes does it have? And that's true. There will always be questions that we can't answer using this, and we don't advocate throwing away the rest of the data. We say absolutely store that, but just dip into that remaining volume of data when you have a very specific question to answer. So to give you an idea of what this looks like, so we operate exclusively in the time series data set. So this is, you can call it IoT data, time series data, telemetry, there's various terms, but they all basically mean the same thing. If you can graph it and you've got time on the x-axis, it's time series data. So if we look at what can you do with 100 to 1 data reduction, this is 1%. If I've only got access to 1% or I can only transport 1% of my data, what can I do with it? So I've been doing this in some way, shape or form for 20 years, and for 20 years there has been the same answer. If I have more time series data to process, store or transport than I have bandwidth available or capacity available, what do? I downsample it. That's the answer everybody uses all the time. Well, averaging or downsampling, we know what it looks like. If we look at the green data here as the original data, and the pink data is the average data, what happens? We lose all of the peaks and troughs and spikes, all of the interesting bits. And if this is vibration data, those spikes and peaks and troughs, those are very likely the ones that are actually telling me the most interesting thing. Those are very likely the ones that are the actionable information I need to jump in and do something with. So we've got accuracy here of probably less than 40%. So how many people want to make business critical decisions on an accuracy which is A, not guaranteed, and B, somewhere less than 50%? With the same data reduction, this is what we have with gallium. Not super clear in this light, but there's an almost perfect overlay between the pink data and the green data, somewhere of order of 99%. And we've got this running live with an IoT example on our booth in the exhibition hall. If we look at that in context, this is a connected car use case. As I said, today we've got a customer who's taking 10 metrics out of 1,000. What would we do? We put gallium at the edge. The edge can be in the aircraft, the edge can be in the car, the edge can be on the cow or on the fence post, the edge can be on the plant in the factory. And we might take 1% of the volume representing 99% of the accuracy, store the remaining on board. We may still additionally need to, or occasionally need to dip into it, bring that back, and that allows all of our analytics, our machine learning and our AI that we're able to do, but we're now able to do it on all of the sensors from the car at 99% accuracy, as opposed to 10 sensors at 100% accuracy. So we're getting a huge amount more business value for the same cost. Or, looked at another way, to the shoestring point, we could say, well, maybe we want 50 sensors, but we actually want to reduce our bandwidth bill by 2 or 3 or 4 times. So there's obviously a trade-off between how much you want to bring back and the cost. This is pure software, so we can deploy it anywhere. We can deploy it in brownfield sites. And we, as I say, we still store the remaining data locally for hookup. In the case of a car, it's when it comes in for service. In the case of an aircraft, it's when it goes in for maintenance or when it arrives at the gate. So I said there were 2 things that were holding all of these use cases back. The first one is that ability to transport data. Let's say you've solved that problem. The second problem is when you take this data from multiple sources, in a single place, it's volumetrically still very, very big. There's a huge amount of it. When we want to process analytics and we're doing it of thousands, tens of thousands, hundreds of thousands of devices, there's an enormous quantity of data. So I don't have the video here, we're playing this on our stand next door, but we take a very, very large data set and we process it twice. We process at 100% accuracy, where a single analytical report, complex, but a single analytical report takes best part of 2 hours. And we run the same analytical report at 99% accuracy, where it takes 9 seconds. So we've got analytical results for a user 700 times faster for less than 1% drop in accuracy. And if you look at it side by side, it's the same information. It's the same decision-making results. But why is that important? Well, the days of being able to make decisions on the output of a single report are gone. If that was the only problem, you say, right, I'll schedule it at 6 a.m. It'll be in my inbox as a PDF when I get there. That's what we did in the late 90s, and we solved this problem just with brute force. The problem is that one-off report is very rarely enough to answer the question. The one-off report might give you a moment. What we want is the aha, where we do something actionable with it. And the journey from to aha is called data exploration. And so if we take that same 6.3 terabyte, 300 billion row, 4.5 trillion data point data set, what we're now doing in this recording is interacting with it in real time. Now, how many people can put their hands up and say, I can interact with a 6.3 terabyte, 4.5 trillion data point data set in real time? Zoom, filter, exclude, go into the data, realize it's a dead end, back out, go down a different path. So we go through 8 different exploration steps in 40 seconds. And this is a sort of frequency that users expect. If you're going to do data exploration and each mouse click takes a minute, the users are going to give up and go somewhere else. Okay, if it seems like this is obvious and someone should have reached this conclusion before, the answer is they have. Snowflake is a preeminent data warehouse, cloud-based data warehouse, reached the conclusion that machine-generated data has a lot of valuable information, but also a lot of noise. There are storage companies, their conclusion is just store it all, which is fine. Microsoft on the IoT platform essentially reached the same conclusion. They even say the words, you've got to sacrifice some precision, but their answer is back to downsampling, back to averaging. We've seen the negative effect averaging has. So we agree with Snowflake and with Microsoft about the problem. We have a different solution and a different premise to that solution. So if I come back to this original assertion, 99% of your data is worthless, but which 99%? The answer is the data that is costing you an enormous amount to transport, an enormous amount to store, an enormous amount to process, and causing your users to wait 2 hours instead of 9 seconds, but is contributing nothing material to decision making. That's the 99% that's worthless, and that's the 99% that we focus on identifying and removing at source. Thank you. Any questions?
Is there a quick question? Yes.
Thank you. It's Shaz from Vodafone. I have a quick question. This sounds great for people that are already pulling back data, but have you thought about people who aren't necessarily doing that today?
Yeah, actually, we've talked to a couple of people here in exactly that situation, and this comes back to the economics. Most people who aren't pulling data aren't pulling it because they haven't been able to create a business case or show an ROI for doing that, and that's partly because to take the connected car, go to your boss, I want to build a business case for pulling 10 metrics and it's cost $1 million a year. It's hard to show that value. Say, oh, I can pull 1,000 metrics and it's going to cost $1 million a year. Okay, the cost is still significant, but again, it's so much more business value. It's much, much easier to prove an ROI to close the business case when you can get, store, process, and analyze a huge amount more data for the same cost. So we're seeing it optimizing people who are already doing it, but also changing the economics for people that aren't able to do it yet.
Just a very quick question. It's normally the case that the closer you put memory to the edge compared to back in the cloud, the more expensive it is. So your model where your car, for example, the car has a server on board is actually going to add quite a lot more cost to the overall solution compared to importing the data back.
So that's great. So when we first started this, our naive assumption was baked is expensive, storage is essentially free. And then in every use case we got into, people said, no, storage isn't free, it's expensive. In the submarines, they measure storage by how many tins of baked beans it takes up, because if you have more baked beans, you can stay submerged longer. So actually, that's one of the big applications of our algorithm is we don't say put additional storage. Say, whatever storage you've got at the moment, maybe you can store 3 days worth of history. We might transport, say, 95% accuracy over the air. We might store the delta between 95 and 99% accuracy on that local storage. Maybe now you can get 3 months or 3 years worth of green buffer there, and the delta between 99 and 100% accuracy throw on the floor. So I agree that the storage at the edge is always an issue, and actually there is a strong use case for our algorithms to not just optimize what's being sent over the air, but what's being stored locally, because typically there is storage. We're mostly working in brownfield sites where it's already out there, but it is enough for 1 or 2 days, not 1 or 2 months.
I think we need to move on, actually. So thanks very much.
Thank you.
That was down as a 10-minute session, so to move on.